Hello, everyone. Welcome to today's ARCHER2 webinar. Today we have Duncan Docker, who is a Royal Academy of Engineering Research Fellow at the School of Engineering at the University of Edinburgh. And he will be telling us all about the hidden world or universe of nanobubbles, including simulations and ARCHER2. Over to you, Duncan.
Uh, that's great. Thanks very much for the introduction, and thank you very much for hosting me for this webinar series. Just a recap, my name's Duncan Docker. I'm a Royal Academy of Engineering Research Fellow, and today, let's see if this animation runs, I'll be showing some of my molecular dynamics simulations revealing what I've described as the hidden behaviors of nanobubbles. So there is a growing industry which claims that nanobubbles can be used for a variety of water and wastewater treatment processes, as well as a wealth of other applications. And this can be done by filling these nanobubbles with ozone gas, which can be used to improve the efficiency of advanced oxidation processes for breaking down bacteria. Or alternatively, if you fill them with oxygen, you can improve the dissolved oxygen content of water, and that can be used to promote the aerobic breakdown of toxic algae blooms, which have quite recently become a recurring blight on British waterways. However, despite what appears to be quite seemingly promising results by industry and industrial case studies, nanobubbles are a surprisingly controversial topic in academia. I've met many quite well-respected academics in this field who tell me that they just don't believe that they exist, and the reason for that, there's actually a few reasons. One is that the classical equations that predict their lifetime should be too short, on the order of milliseconds, to have really any effect in these applications, or even just be observable. And it's still unclear the fundamental mechanisms why they should be stable, as well as any of their potential disinfection capabilities. And to top all that off, in experiments, direct measurement of bulk nanobubbles is very difficult. So experiments can typically only show indirect evidence. That's usually by some process like dynamic light scattering or zeta potential measurements, which can show the presence of some nanoparticles in solution, and then potentially showing that these effects change or disappear after you degas the solution. But experiments really struggle to truly conclusively prove that they have nanobubbles present. Despite that, there are some people who are very adamant that they exist and they're performing a beneficial application. This is the case for bulk nanobubbles. These are spherical nanobubbles within the bulk liquid. However, around 10 years ago, what was found was a mathematical proof for stable surface nanobubbles. So these are bubbles that sit on a solid surface, and they have this kind of hemispherical shape. And there's essentially two criteria for their stability. One is a supersaturation of dissolved gas within the surrounding liquid. But then more crucially, at least for my work, is this what's known as contact line pinning. So this is where the gas, liquid, and solid phases all meet at this edge around the perimeter of the bubble, and it's pinned in place either by some sort of surface roughness or chemical heterogeneities. In this case, it's a hydrophilic and a hydrophobic substrate. And this contact line pinning results in a different growth mode than is typically seen in bubbles. One's called the constant contact radius growth mode. So essentially, this lateral diameter is pinned to the surface. And the result of this, we'll go into a bit more detail later, but it essentially sets the surface nanobubble in a negative feedback loop, which gives it a diffusive stable equilibrium. Now, more specifically, I'm interested in cavitation. This is the phenomenon where bubbles can experience unstable growth and then violent collapse in response to a pressure wave. I like to think of cavitation as like the flip side to boiling. So in boiling, we increase temperature until we start getting these vapor bubbles forming the surface. Where pressure, instead of raising the temperature, we're going to drop the pressure in our solution. And that might seem a rather trivial distinction, but it actually has quite big implications in engineering. So if you think about boiling your kettle, that might take several minutes to reach temperature of 100 degrees. But pressure can fluctuate many hundreds, thousands times a second. Just me speaking to you are fluctuations in pressure. We can also see this in turbo machinery, where cavitation is quite a significant problem. So as a ship's propeller spins, you get these large fluctuations in pressures, which are cyclic. And during these low pressure phases, these bubbles can form, and they expand rapidly. And then as the pressure reaches a maximum again, these bubbles start to collapse. And as they do, they don't collapse completely spherically. They have this jet that forms towards preferentially one side, which can impact the upper bubble surface. And then if this jet impacts the solid, it can result in pitting damage. And one bubble alone is unlikely to do all of this, but you have to think of a scenario in suboptimal conditions where you have a propeller spinning many hundreds of times per minute. And if you're repeatedly producing these bubbles, you're going to end up with repeated jet impacts, which result in gradual erosion. And the worst I've heard of this is pumps lasting maybe a matter of months before they've completely destroyed themselves by cavitation. So obviously a big problem in some parts of engineering. However, if we can harness this quite powerful jet impact, we can potentially use cavitation for more beneficial applications at the nanoscale. So for example, as we've already seen, bacterial and wastewater treatment, if we can get this jet to impact a nearby bacterial cell membrane and we can break it up and potentially destroy whatever parasitic cell is in there. Or we can use these jets to remove and dislodge debris and particles from microfluidic devices that might not be as reachable with larger bubbles or other cleaning devices. So when surface nanobubbles were discovered, it seemed natural to assume that they were the nuclei for cavitation. However, there were many cavitation models that had already been predicted previously, and we found that they were not suitable for surface nanobubbles. So we can have a look at the example here. We have the Blake threshold. This is the pressure drop required to induce an unstable expansion, essentially the onset of cavitation. And it depends on its vapor pressure of the liquid, which is negligible, surface tension, this exponent K, which comes from polytropic equation, its initial radius, initial gas pressure, and all these will be elaborated more in time. But just to say that this equation holds well for spherical bubbles and spherical nanobubbles. You see, if we apply it to this bubble, it becomes unstable. It just keeps growing unbounded and eventually outgrows the whole system domain. But if we were to apply this Blake threshold to a surface nanobubble, what we see is that this bubble has grown slightly, but it's just reached a new stable point. So the bubble still remains stable and has not undergone cavitation. So the immediate question is how do surface nanobubbles cavitate, or more specifically, how does this constant contact radius growth mode affect their cavitation dynamics? For this, I've been using molecular dynamics simulations. So there are alternative ways of modeling nanobubbles, obviously. When you think of fluid mechanics, we might be tempted to think of the more conventional Navier-Stokes or continuum-based CFD. The issue with that is that at the nanoscale, we have many different effects that need to be incorporated. So things like surface tension, multi-phase flows, diffusion, slip, non-equilibrium gas dynamics, all of which are possible to implement in continuum-based CFD, but they all carry certain numerical approximations or risks of introducing instabilities in the simulation. Whereas molecular dynamics naturally captures all these effects organically. We can see contact line stick and slip motion and surface tension, just with a couple of parameters surrounding the interactions between molecules. So molecular dynamics is ideal for modeling nanobubbles and gaining some insight into some of their non-trivial behavior. However, the caveat is that MD is a very expensive simulation tool, and we really are reliant on using HPCs for simulations. And as you can see, these size scales and length time scales are extremely small. So We are very reliant on using HPCs like ARCHER2, which I'm very grateful that most of these simulations today are run on that. But we also have to be very strategic about what we're modeling and how we can use that understanding to scale it up to more experimentally relevant conditions. So as a quick summary or background behind molecular dynamics, we're essentially modeling the trajectories of atoms which all interact with each other via these interatomic potential functions. The most common ones are the Lennard-Jones potential, given here in blue, and the Coulombic interaction. Lennard-Jones captures interaction between uncharged atoms, so that's the majority of atoms, but Coulombic interactions can also capture electrostatic effects. So for example, we have water molecule, which is polar, so it's neutral, but it has a non-uniform charge distribution, which can only be captured by this Coulombic effect. And electrodynamics, for as complex and as high powered as it really is a simple case of taking this potential function, finding the force by taking the derivative with respect to radial distance, and summing up the forces on each atom at each time step to determine its acceleration. So we're essentially applying Newton's laws of motion at a very grand scale. So on the right here just shows a typical simulation that I have set up. We have our nanobubble on the surface, which is composed of a two-site nitrogen model gas phase, surrounded by this TIP4P 2005 liquid model, which captures Coulombic interactions. It's also pinned to this substrate. So as you notice, it's got this gray and yellow patterning, which is a hydrophilic and hydrophobic substrate patterning, which allows for this contact line pinning, which is essential for their stability. And then finally, because we're interested in cavitation, we can control the pressure in the system by the application of a piston in which we apply a force to it. So in this case, we apply a force of 1 megapascal. That should be reflected on the pressure that's measured within the liquid phase. So as well as being computationally expensive, MD also outputs very large data files that can range anywhere from a couple of or tens of megabytes up to hundreds of gigabytes per case. There are some third-party software available to analyze these data files, but rather conveniently, this data really is just at each time step a Lagrangian coordinate position of each atom as well as velocity. It's rather simple, and for that we can analyze it with rather simple post-processing. And usually to do that, we'll define like a C++ script to read through all the atomic positions and sort all the atoms within a series of bins. So we'll create this this mesh-like structure of bins, and within each bin we can sum or take the average of all the atomic properties in there and end up with a data file which is much smaller, a lot easier to work with, and gives a more of an intuitive reflection of what's going on in this nanobubble. So I'll just quickly go over some of the measurements we can take. We can take the density, which is essentially just the sum of the masses of the atoms in each bin. And for the nanobubble case, we can define this interface by this 50% isodensity contour. That's between 50% between the liquid bulk density and the gas bulk density. We can also take the mean flow velocity. That's the weighted mean velocity of all the atomic velocities in each bin. But what's also important to remember is that we're taking averages, which is a very statistical process. So as long as a mean, we have a variance in velocity. And this variance in velocity, which is related to its standard deviation, actually gives us a measure of temperature. So from just velocity, we can capture mean flow velocity as well as temperature. Now, finally, I think perhaps most important for this work, we can measure the pressure, and we do that using what's known as the Irving-Kirkwood virial stress tensor theorem. And this has some quite important implications for some of the cavitation models we'll be discussing, so I think it's worth delving into. But essentially, pressure is composed of two components. We have a kinetic component, which is what we usually think of when you think of pressure, and this is like the thermal energy of the molecules and how they bounce around and they impart momentum on each other and on the surfaces of walls. And then we also have this virial component, and this captures the interactive forces such as from the Lennard-Jones and Coulombic potential, but not just the collisions. They capture the short range attractions as well. And because of that, they become more dominant in dense media such as liquids and solids. Now, strictly, this virial pressure theorem is really only suitable within the bulk of phases, so towards the center of this liquid and gas phase. Closer to the interface, these stress tensor components, they diverge. So we can't measure pressure, but what we can obtain from this is a quantitative estimate of surface tension. And this is very useful in terms of applying our analytical models for cavitation for comparison with our molecular dynamics results. Now, there's a quick caveat that I have to make before we can move on to looking at some actual simulations. In my opinion, this becomes one of the main hurdles behind cavitation and why I think it's not so well understood in the literature. So our models that we've been looking at, such as the Blake threshold, that will predict a cavitation threshold of around -1 megapascal. And that's an absolute pressure value. So that's 1 megapascal below zero and not a gauge pressure, as we might assume. This seems to trip up a lot of people, and I've had a lot of debates with people about this. Our intuition of pressure comes from Boyle's law, but this is really only true for gases. And as we described in the last slide, the pressure in gases is purely kinetic, so it arises from the intermolecular collisions of molecules bouncing off each other or off the surface of your domain. However, for dense media like solids and liquids, this pressure is dominated by intermolecular attraction, or these closer intermolecular forces, and pressure instead is dominated by this virial pressure component. And essentially, while you have some degree of attraction between molecules, it does mean that liquids can sustain some amount of tensile stress or negative pressure before they rupture. And this is possible for short time scales. So it's not a thermodynamic equilibrium. It's not in conflict with what we understand about pressure, but it's just to say that these negative pressures exist short enough that they have an influence on cavitation, and they are stable enough that compared to the kilohertz to gigahertz natural frequencies of bubbles that are observed in cavitation, that they are fine. But longer term, over macroscopic timescales that we're used to seeing, we can't observe a negative pressure. We can actually see this in MD. So taking this piston effect, this piston case without a bubble now, if we move this piston upwards, apply an upward force, and we can actually go into this regime where we get a measured pressure, which is in good agreement with our applied upward pressure. Just one last, I think, point to try and sell people on this if they're still skeptical. Negative liquid pressures are not in thermodynamic equilibrium. In a sense, they're actually equivalent to being a superheated liquid. So instead of superheating our liquid, where we go from this point to this point in our phase diagram by heating above the saturation temperature, with negative pressures, we can drop this pressure below the saturation pressure and actually reach the same equivalent thermodynamic state. So if you're unsure about negative liquid pressures, you can just think of it in terms of a superheated liquid, and that will be, in my opinion, that's enough to justify its existence. Right, with that out of the way, let's look at some simulations. So my work follows roughly the dynamic process of a cavitation bubble. So first of all, we have to look at the inception process, or when does a bubble become unstable? So for a bubble to be in mechanical equilibrium, that means its pressures must balance across the interface. So we have an external liquid pressure P infinite, and that must balance this internal gas pressure Pg, which is a function of its volume given by this polytropic exponent equation. Some vapor pressure of the liquid phase, but it's negligible, so we're not going to discuss that too much. And then the most dominant component is from the surface tension, actually, or known as the Laplace pressure. So this is this 2 gamma over r term. And essentially, as the radius decreases, going towards the nanoscale, this gas pressure from the Laplace pressure becomes very high. It can be from 10 to 100 atmospheres. So to induce unstable cavitation growth, what we need to do is reduce our external liquid pressure below a certain threshold, below which it's impossible to achieve mechanical equilibrium. And at this point, will achieve a rapid unstable growth of a bubble. And we can see that here. We drop the liquid pressure, the bubble grows, but inevitably this liquid pressure is going to return back to its initial value. And as it does, we get this very sharp and violent collapse of the bubble, which ends in these very non-linear rebounds before reaching its equilibrium value again. And this can actually be predicted by another one of the most famous equations of cavitation, the Rayleigh-Plessed equation, which captures the inertial and viscous response of a spherical bubble from these external pressure changes. So as a quick introduction of where this cavitation threshold comes from, we can obtain the Blake threshold by looking at the Rayleigh-Plessed equation and taking all the time derivative terms to zero. Or we can look at this graph and perhaps give a bit more intuitive explanation of what's occurring here. So we have a spherical bubble first we'll look at. As it grows, its radius increases, which means its volume increases, and naturally by this polytropic equation, its gas pressure will decrease. And we'll notice for this bubble, as it's increasing, its radius of curvature also increases, which means this Laplace pressure term will decrease. And if we subtract these values, we can obtain a range of liquid pressures at which this bubble can remain in mechanical equilibrium. And the minimum of this point is known as the Blake threshold. So if we drop the pressure below this point, we'll get no cases of a bubble being stable for a given internal gas pressure and Laplace pressure, and it will grow unbounded. If we look at a surface nanobubble case now, though, we start off with quite a low profile nanobubble, and you notice that its radius of curvature is actually very large. And as it grows, its radius of curvature decreases. So this is the opposite of what we were seeing for the spherical case. And it means that as the bubble grows, its radius of curvature decreases, and therefore this Laplace pressure term increases. And if we find the new range of liquid pressures now that can sustain this surface nanobubble, we find that this new corrected cavitation threshold is much lower than what we were seeing for the Blake threshold. So this is all theory. Let's see it in action though. So I have, this is one of the first pieces of work I did. This is for a 2D surface nanobubble on a surface. And running many simulations, but we'll just focus on the two key ones here. We have either side of this predicted threshold, which is about -3.8. I'm going to run two cases here. The case on the left is just above this threshold pressure, and we see it reaches a stable size and then it just stops. But if we were to drop that pressure any lower, the bubble suddenly keeps growing and unpins from the surface. And if we look at all the stable cases, we find it follows this predicted line very well. We have this jump, which occurs from this subset B to C, as the nanobubbles pin from one site and unpins to join the next site. And then below this mark here, this cross represents the absolute lowest pressure that can sustain surface nanobubble. You notice these are all significantly lower than the predicted Blake threshold. That's for our 2D case. We can now scale this up to 3D. This was run on Archer, so predating ARCHER2, where we had less computational resources available to us. So I only got two cases to show you here, but one is either side, again, of this cavitation threshold. And as we see again, as the simulations run, we have one case on the left where just above this threshold, the bubble is stable, and just below this threshold, the bubble is unstable and continues to grow out. And what you'll notice is that these pressures are quite a bit lower than in the previous slide. That's because going from 2D to 3D, this Laplace pressure term here essentially doubles. So the internal gas pressure of the 3D case is about twice as large as it would be for the 2D case for the same size bubble. So the implication from that was that surface nanobubbles, despite being potential nucleation sites for cavitation, they don't obey by the same dynamics that we expect from the classical cavitation models. So beyond the inception of a cavitation bubble, we then get its very rapid growth rate. And as well as that growth rate, we also have sometimes very non-linear oscillations. So bubbles, we can actually think of them like damped oscillators. We have an internal gas phase, which acts like a spring, and an external liquid phase, which represents the inertia of the system, as well as providing some viscous dissipation, most dominantly at the liquid-gas interface. And if we take this Rayleigh-Pleasant equation, we can linearize it and obtain what's known as the Monod frequency. Now, this is the actual frequency for a bubble. And for a very small nanobubble, we're in the gigahertz range, but beyond, up above for micron to millimeter size bubbles, we're in about megahertz to kilohertz range. So we'll often talk about bubbles undergoing ultrasonic excitation, and that's because their natural frequency is typically in the ultrasound range. So as we saw, the Blake threshold equation didn't capture the pin growth of surface nanobubbles, and it's also unlikely that the Rayleigh-Pleasant equation will as well, because it assumes a spherical bubble. So we took the Rayleigh-Pleasant equation and transformed it into this volume form. So it's basically the same equation, but in terms of a volume coordinate instead of a radial coordinate. And then used the volume for a spherical cap, growing by this pinned method for the inertial and viscous terms. And then this pressure balance we just used from the same equation that we'd used in the previous work. And if we linearize this equation now, we can obtain a new natural frequency model for our surface nanobubble, which is, instead of the radius, it's given by this contact diameter phi, as well as this contact angle of the gas phase. And again, that's the theory, but we can test this with MD. So to do this, we took this simulation. You might notice this is quite large compared to the previous case. That's because to correctly capture the inertial of the liquid, which should be a far field sort of semi-infinite domain, we had to expand this. We weren't capturing the correct inertia with the much smaller domain. This did also limit the size of the oscillations that we could realistically input into the system. But we apply a sinusoidal forcing to this top piston, which results in a sinusoidal response in the nanobubbles. And if we looked at the amplitude of that response, we get all these data points here, which is in pretty good agreement with our linearized model. So we have a natural frequency, but because this is a highly damped system, the peak oscillation is actually closer, or actually lower than this natural frequency. But again, is in good agreement with our analytical model. And we can compare this as well to some of the previous models used in literature. So we have the Monod frequency for spherical bubbles, Blue's frequency, which is for unpinned surface bubbles, which you might have thought would be close to our case, but didn't quite match out. And then also this Miller-Nyborg model for gas within a cylindrical micropore. And we notice that these natural frequencies are all well below even this peak driving frequency, which suggests that they're not capturing this behavior properly. Now, there's a particular point of interest in this graph. There's two limiting assumptions for the nanobubble behavior. One is that the gas phase would oscillate adiabatically, which is in good agreement here. The other is if the gas was isothermal, which wasn't as good agreement. But I'll explain in a few more slides why this is potentially interesting and what potentially anomalous behavior is going on. So taking a step back from these surface nanobubbles, and we're just going to look at a more fundamental spherical bubble case. I was discussing this adiabatic or isothermal limiting behavior, and it seemed like it was worth testing because this was in contradiction to what was being suggested from theoretical models. So again, we're going to run some cases where we have a piston that moves up and down sinusoidally, which can induce sinusoidal variation in the bubble radius, pressure, and temperature. And then from the radius and pressure, we can fit to this polytropic exponent gas law to get this value of K. And K traditionally should be between a value of 1, which is isothermal, or about 1.4, which is, or in more fundamental terms, the ratio of the specific heat capacities, which is 1.4 for a diatomic gas. Now, there's been some models which can predict this for oscillating bubbles, and and it's found that it's a function of the Piclet number, which is a ratio of conductive transport to diffusive heat transport. For low Piclet numbers, essentially low frequencies, we'd expect isothermal behavior, which is just to say the bubble is oscillating slow enough that there's enough time for heat to transfer between the liquid and the gas. Whereas if you increase this frequency, you get to more adiabatic behavior, or in other words, there's not enough time for heat to transfer between the liquid and gas phases, and we get these temperature variations within the bubble. Now, one model here assumes that the pressure inside the bubble is uniform. There have been other developments to this model to look at non-uniform pressure. And what happens as these bubbles oscillate, we have these standing waves develop within the gas phase, which cause interference patterns and change the effective polytropic exponent K. We get this peak, which roughly corresponds to a Mach number of about 1 in the gas phase. And you'll see that for nanobubbles, this is specifically for nanobubbles. For larger bubbles, this peak is closer to its adiabatic limit. For nanobubbles, we shouldn't really expect much more than isothermal behavior. However, when we ran the MD simulations, we see completely non-trivial behavior and what looks like an adiabatic maximum, which is currently unexplained by these theoretical models. So there's two reasons for this. One is that we have a non-ideal gas, which can be better represented by the van der Waals equation of state. But then also we have the rather confusing effect of non-equilibrium gas dynamics. So non-equilibrium gas effects can be characterized by this Knudsen number, which is a ratio of the mean free path to the bubble radius. And this manifests as a temperature jump at the liquid-gas interface, which is proportional roughly to heat flux, or in other words, the temperature gradient just at the interface. So if we take both these effects into account, we get pretty good agreement now with the variation in temperature across the bubble, or the oscillation in temperature across the bubble. And if we were to derive an analytical equation for this polytropic exponent K, we find that taking both these effects together again, we get really good agreement now with these MD results. However, we might see something that seems a bit peculiar at first, and that is that at this lower limit, we're expecting isothermal behavior, but we're not seeing this value of K equals 1, which is what we would expect. As it turns out, this value of K to 1 to 1.4 is really only true for an ideal gas. And as we go to a non-ideal gas, these limits change. So it goes from an isothermal behavior at this coefficient W, which is related to the density and the pressure, and then also an adiabatic limit, which is also a ratio of the specific heats, but this ratio changes or increases for non-ideal gases. And if we take these two new limits now, we see that even though we're getting good agreement, and even though it's that if we view it from an ideal lens, this polytropic exponent appears adiabatic, the nanobubble behavior is actually truly closer to its isothermal limit. So this adiabatic behavior that's been referenced in my work and also previous works is a bit of a misnomer, and is really only just a misinterpretation of the variation in pressure and radius. However, despite this van der Waals effect, this temperature jump from the non-equilibrium gas effect, this still does promote some adiabatic behavior, but it's not enough to get it up to a fully adiabatic system. So we have looked at the inception and the rapid oscillation and growth dynamics, but now comes perhaps the more engineering relevant part of cavitation. It's how they collapse again. So because of the high effects of viscosity at the nanoscale, this jetting collapse is not actually as common as you would see in the collapse of larger bubbles. We can actually only generate this jetting motion using shock waves. That might sound like a bit of a cheat, but in reality, when you have larger bubbles collapse, they release shock waves because their collapse is so violent. And this can have a cascading effect where these shock waves collapse smaller bubbles, which then collapse and release more shock waves, and it propagates down into the nanoscale. And so this shockwave incoming might be arising from a larger bubble collapsing. So it's not a completely unphysical situation. Now, with the benefit of MD, I said we can model liquids and solids, liquids and gases very well, but we can also model solids. So in this case, this is an amorphous silicon slab, which is deformable. And we're going to look at some simulation cases where these different bubbles collapse on this flexible solid, and we're going to see the resulting damage. So we have a case on the left, a spherical case, the kind of classic case. Then we have two surface nanobubble cases, one which had a high contact angle and one which had a low contact angle. And I think visually it's pretty evident already that there's quite significant differences between the final pitting damage. And this concentric pitting sites weren't actually essential for the spherical cases, but they are useful in letting us visualize damage. So I left them in for this piece of work. So all the bubble collapses produced pits, and these pits had a kind of spherical cap indent shape. There's some interesting scaling going on here. So we have a lateral diameter of the pit, which roughly matched the diameter of the bubble before collapse, and that was true for all bubbles. However, that's where the similarities really ended. So for the pit depth, we found that as the bubble increased in size, the pit depth also increased in size. For the surface nanobubble cases, the pit depth was really only dependent on the initial contact angle. So the high contact angle case had certain pit depth, low contact angle case, pit depth was pretty minimal. I think what's apparent as well is that the spherical cases produced a lot more atomic debris removed from the surface. So you might be thinking why that's the case, because the surface nanobubbles are closer to the surface. You might think that jet impact would be higher. We can look at the velocity fields going on during this collapse. So if you look at the spherical bubble first, we have a z component velocity, normal to the surface on the left, and a radial component velocity on the right. And what we notice is that the jet forms, we have this high velocity moving down towards the bubble, but also this recirculation of flow around the bubble that results in this curved jet profile, which when it impacts the surface, pushes out again afterwards, and we get this sort of punch and drag motion where the rotational momentum of the fluid is conserved and moves outwards again. If we look at the surface nanobubble case now, what we see is that as the bubble collapses, the solid's essentially blocking this development of the jet. So the jet's already impacted the solid, whereas the time to fully develop. And aside from this, we also have not as much recirculation of fluid flow around the bubble. So as the jet impacts, we don't get the same outward flow, and instead it appears more like almost like a planar shock wave impacting the surface. So in terms of quantifying all these effects together, pressure is not always the best metric to use for quantifying damage, because this impact is such a rapid dynamic effect, as well as the fact that in molecular dynamics, pressure can be quite a noisy measurement. It turns out it's actually better to measure in terms of impulse, which is just the time integral of pressure, and we can measure that across the surface of the solid as the jet impacts, and we get this spherical or this cylindrical pattern, which we can sum for all the bubble cases. And what we find is that there's a peak impulse near the middle, and this peak impulse roughly corresponds with a linear relationship with the final pitting damage of the pit. I've not been able to look at this in more detail, but it's definitely something I'd like to resume again, because I think this is potentially quite an interesting effect, or might scale up to larger bubbles where this modeling of solid interfaces is not as easy to implement. So this video, this is a little bit of a plug for myself, but if this looks familiar, I actually submitted an earlier version of this work to the ARCHER video competition in 2019. and this was runner-up, I believe. We can see this this bubble collapse in a bit more stylistic way, where we see the jet impact the surface. We have this the atomic debris removed, and then I perform what I described as the MRI scan, where we can see the resulting pitting shape in the solid. And if anyone's interested, I'll leave you to follow up on that on YouTube if you wish to see more. Right, so leaving cavitation aside just for a moment, there became a much more pressing issue in nanobubble science since doing that work. And that was the nature of stability. So we've so far been discussing surface nanobubbles as the only nanobubbles which can be stable long term. However, recently there's been growing claims for bubbles to exist within the bulk, and this is also coming from these nanobubble companies who are producing pumps who claim all these magical improvements in water treatment. Now, the experiments which are by people who are suggesting that bulk nanobubbles exist, they will consistently report a zeta potential of around -10 millivolts, which suggests that these nanobubbles are like charged particles. And the argument that followed from this was that this zeta potential arises from ions absorbing onto the nanobubble surface and forming an electric double layer around the nanobubble. And crucially, these ions on the surface would exert a repulsive stress or repulsive forces on each other, which would manifest as this electrostatic stress, which actually relaxes the Laplace pressure. So the internal gas pressure would not be as high as it would be otherwise. And you might be questioning what the motivation for that would be, or why that would be important. If we look at this equation, this is no longer Rayleigh-Plesset equation, this is Epstein-Plesset equation, and this describes this lifetime of bubbles, which is become so controversial or contentious in this field. Epstein-Plesset theory essentially captures the diffusion equation in spherical coordinates. So we have essentially a boundary condition at the bubble interface, where this concentration is proportional to the internal gas pressure by Henry's law. And as the bubble shrinks, this gas pressure increases, which in turn makes this this gas concentration go up. So essentially pushes more and more gas out as it shrinks, which puts it in a positive feedback loop and essentially an unstable equilibrium. However, if there was a way to reverse this process, so as the bubble shrinks, the gas pressure also shrinks, it might be possible to induce a stable equilibrium by Epstein-Plesset theory. And that's what we can see here. And this is what, theoretically, this electrostatic stress is doing to these nanobubbles. However, this model came from a lot of theoretical work, not proposed by myself, proposed in literature, and it's often backed up with experimental measurements of zeta potential, but it never really been investigated thoroughly at the nanoscale. So that's what we decided to do in one of our most recent pieces of work. What we found was a little bit surprising at first. I was admittedly skeptical of this theory, but we did find that sodium and iodide ions in solution, they did absorb onto the nanobubble surface. So we're looking at the liquid density side. This is the interfacial region of liquid gas interface, where we have this non-equal variation in sodium and iodide ions. Then just beyond the interface around here, we have this electric double layer region where we have this variation in sodium and iodide, which is not uniform, which then extends towards the bulk liquid phase, where we recover this uniform ionic concentrations. And the width of this electric double layer, it can be characterized by this dBi screening length. So with these positive and negative sodium and iodide ions, we can sum up the charges to get an ionic charge density. Again, we have this electric double layer, and we see this what looks like a non-uniform charge, and then take the integral of this to find a surface charge density on the surface. And this peak surface charge density, or the square of this peak surface charge density, happens to correlate very well linearly with the concentration of dissolved ions. And very conveniently, we can use this analytical equation here to define essentially a single mean value of zeta potential of the nanobubble. And in this case, it's around negative 8 millivolts, which is comparable to the negative 10 millivolts that we're seeing in experiments. So far, this equation, this electrostatic stress model seems to be holding water. But here comes for the crucial test. Can we actually see this electrostatic stress manifest? So what I'm showing here, these data points for now, I'm just going to say these are just for the no ion cases. So this is what we'd expect. We're going to measure the pressure difference. That's the difference between the gas pressure and the surrounding liquid pressure. And this should be equal to the Laplace pressure term that we're used to seeing by now. And then this hypothetical electrostatic stress term. There is some correction we have to make for the Tolman length. So that just says the surface tension reduces slightly for smaller bubbles and droplets. But it's the same, it's going to act the same for all the ionic cases. So this red line is our true Laplace pressure curve. But when we add the ions, what we were expecting or hoping to see is that they would fall along these lower dashed lines. That's the effect of this electrostatic stress. But instead, they all fall on the same line. So this pressure difference is governed just by this Laplace pressure term, and there's no evidence for this electrostatic stress, which would seem to contradict this this popular model for electrostatic stabilization of bulk nanobubbles. So you might be asking why that's the case, because we did see some evidence that there was a zeta potential and ionic layering. It's important to remember that while ions were exerting some sort of charge density across the bubble, water molecules themselves also have a charge density. So they are neutral overall, but because they are polar, they have a unique non-uniform charge distribution across their surface. And with the addition of ions, we can see that the water molecules change their orientation to account and essentially negate any net charge that might arise from this ionic layering. And if we were to look at the total ionic charge density now, so that's both no ions and ions, we see that there's very little difference now, negligible difference basically between the net charges. So the addition of ions seem to make negligible difference to the charge on the nanobubble surface, and really put into question this electrostatic theory surrounding nanobubble stability. This might not seem controversial to people who are not aware of nanobubbles, but this was quite a big talking point, not my work, but this electrostatic stabilization theory was quite a big talking point in nanobubbles for a few years. My work is actually, or our work is disputing that, but then comes the caveat is what could be stabilizing these nanobubbles. So we had to provide some sort of explanation, or what we believe might be a viable explanation for these nanobubbles to be unstable, or stable, excuse me. And to that, we looked at the effect of surfactants. So surfactants are molecules that can rest on a liquid gas interface and reduce the surface tension. If we increase the number of surfactants, we increase the surface excess, which is essentially can be thought of as the number of surfactants per unit area on the interface. We're using the C12E6 non-ionic ethoxylated alkyl surfactant, and if we increase the number of surfactants, we see that the surface tension generally reduces until we get to this value here, which point it becomes constant. And this physically arises from something known as the critical micelle concentration. That essentially means that as you add more surfactants, instead of absorbing onto the surface, these surfactants instead prefer to form these micellar structures or aggregates within the bulk liquid. Now, if we run the same simulation I was showing a few slides back, we're looking at the pressure difference in the bubble. We don't have this electrostatic stress term, but we do have this varying surface tension term. And surface excess varies with the surface, the number of surfactants per unit area. So it also varies with the bubble radius. So as these bubbles shrink, the surface excess increases, and we can actually reach this regime where the gas pressure will decrease as the bubble shrinks. And this is rather critical for this potential stability mechanism that's been discussed for nanobubbles. So we're potentially satisfying one criterion for Epstein-Plesset diffusive stability, but we are assuming, or taking quite a significant assumption, that the number of surfactants on the bubble surface remains constant during this dissolution process. This is one limiting behavior. The other limiting behavior of this would be that instead of constant number of surfactants, we have a constant surface excess for a given surfactant concentration in the bulk liquid, which is given by Gibbs absorption equation. So if we had a constant surface excess, we have a constant surface tension, and the bubbles again would remain unstable. So it's this varying surface tension which would potentially give stable nanobubbles. So we have two limiting behaviors. How do we know what regime we're in? To do that, we've not come up with a conclusive proof, but we've come up with some arguments that might to argue our case. If we look at different timescales here, so we have the nanobubble diffusive timescale. This equation gives roughly the lifetime of these bubbles as defined by the Epstein-Plest equation. And we can compare that to the micelle dissociation timescales. These are the timescales roughly for these micelles of surfactants to completely break up. So it's a equivalent description of how long surfactants can last on an interface. And if we look at these experimental values of nanobubbles that all use surfactants, we see that there's a radius range up to about 300 nanometers. And this has a corresponding diffusive timescale, which is all below this micelle lifetime, characteristic lifetime of popular surfactants such as STS. So again, it's not conclusive proof, but the alignment here does suggest that there is some way that these nanobubbles which have surfactants, their lifetimes are tied to at least the lifetimes of the surfactants absorbed on the surface. So that's everything I have done so far basically on nanobubbles, but I thought it would be a good opportunity to discuss where I think the future of nanobubble molecular dynamics simulations are going. As we know, ARCHER is coming to the end of its life, or ARCHER2 is coming to the end of its life, and there's a promise of new generation of HPCs that I think would be very interesting to apply to nanobubble research. So quite clearly, the big open question remains is why or if bulk nanobubbles are stable. MD simulations can reveal some of the highly detailed properties around the liquid-gas interface. However, we are still very much limited to these small domain sizes and timescales, and we're never really going to, at least in the next generation or next couple of generations of HPCs, I think, we're never going to approach anything close to these theoretical lifetimes of milliseconds, let alone these experimental lifetimes of days to weeks of nanobubbles. Some people then seem to write off molecular dynamics as being too computationally restrictive for modeling nanobubble stability. However, I believe there's still much to learn. While we're unlikely to conclusively prove of bulk nanobubble stability through a single simulation, we can still investigate some non-trivial nanoscale effects and then implement these into multi-scale models, which might still yield a conclusive or a well-accepted argument for nanobubble stability. And these effects might include non-ideal, non-equilibrium gas effects, as we have seen previously, thermal effects such as the exothermic dissolution of ethanol and water, local solubility and diffusion coefficients in water ethanol mixtures, as well as the interaction of many bubbles together in this phenomenon you might have heard of as Ostwald ripening. So last slide for me. Just as a quick summary, cavitation is a complex phenomenon where rapid dynamics and small scales make it very difficult to visualize and correctly understand. However, for molecular dynamics simulations, we can reveal some very crucial behaviors surrounding the initial nucleation of cavitation bubbles, the rapid growth and nonlinear oscillatory dynamics, as well as their violent collapse, excuse me. Beyond cavitation, the other hotly debated question at the moment is whether these nanobubbles that have been reportedly shown to exist in some experiments, if they're genuine. Again, molecular dynamics simulations can offer crucial understanding surrounding these possible stability mechanisms and maybe even provide evidence, or at least indirectly, for a valid and well-accepted stability mechanism. And with that, I would like to say thank you to all my collaborators, to the University of Edinburgh and Royal Academy of Engineering for supporting my research. And as well as I think a big thank you to EPCC and ARCHER2, who has provided or has provided a lot of support with most of the simulations you've seen here today. So again, it's a great privilege to be able to discuss my research on this platform today. Thank you very much.
Thank you very much. Fascinating to see some of these experimental, not just experimental investigations, but definitely trying to understand nucleation, cavitation, lifetime, all these questions from the perspective of simulation. So everyone who's attending, please feel free if you have any questions that occur to you to put these into the chat for Duncan. I mean, this is all new to me, so I'm very interested to learn about this. I have a few questions, and I can ask. Well, everybody maybe thinks about what they're wondering about. I was wondering about some of the boundary conditions that you described for these pinned nanobubbles. So you had this very particular patterning, which had this, the gray-yellow patterning. So that's to create, I guess, to set the contact angle, the contact angle change. Okay, to set this pinning. So how does that boundary condition relate to realistic, experimental, or observed situations?
So it is, I mean, in this case, it is a slightly artificial setting. So this patterning is a very hydrophobic than hydrophilic patterning, which to give us good agreement with analytical models. But this doesn't have to be necessarily hydrophobic or hydrophilic, just any sort of particulate matter on the surface, which is ubiquitous and unavoidable in experiments, can cause this pinning effect. So it's been shown on roughness. So no surface is perfectly atomically smooth. There'll always be some imperfections or grain boundary which can act as this roughness point for contact line pinning. There could also be some sort of impurity on the surface which acts as this like a hydrophobic or a hydrophilic point for which the bubble to attach. So while this is a very idealized case, in reality, surface nanobubbles have been shown to exist quite routinely on surfaces. They're more likely on hydrophobic surfaces with elements of roughness, but it's still a genuine effect.
Okay, and I guess it's already sort of understood that the specific patterning that you've chosen is in no way the results from that are generalizable and doesn't really change, maybe not quantitatively even, but certainly not qualitatively any of the conclusions that you're drawing. So there's nothing reliant on any specific patterning length scales over which you set that up.
Yeah, so that's a good point. So I've not investigated this. Some people have investigated this droplets, where they also look at patterning, and they looked at very narrow patterning to very large patterning. For the very narrow patterning, it was essentially one row of hydrophilic atoms and one row of hydrophobic, and that essentially becomes like a quasi-uniform surface. So you don't see pinning. If you were to increase this distance for larger pinning sites, that's fine so long as the bubble remains on one pinning site. In one of the papers I did, I looked at the bubble jumping to multiple pinning sites, so it does complicate the analysis slightly. But for this simple case of constant contact radius growth, where the bubble assumes to stay on the same pinning site, it's rather irrelevant beyond how big these jumps between pinning sites are after that.
Okay, that's clear. I was curious also what software are you using? Are you using one of the established MD packages? Are you using any custom code? And also related to that, sort of come for your computational runs, what are how many nodes, how many cores are you using for some of the largest runs, for example?
Yes, so I should make clear this is all run in labs. We've had some we have as a group implemented some custom potentials for the water models. That is to get by without using long range solvers and all the simulations. I'm now using long range solvers now, but previously for efficiency we were using a slightly more efficient solver which didn't need these long range corrections. If that means anything to people use molecular dynamics. And yeah, so on ARCHER2, the largest cases I've been running have been the latest cases. We can see these cases here. And each case, I'll have to try and get this right, but I think each case here had 50 nodes run for about 24 hours. So they're big simulations. And I have made use of the low priority queue on Archer for some of these purposes. But they are big simulations that require significant computational power. And as I said, we are very much reliant on the use of Archer because even with a tier 2 or tier 3 HPC, it does slightly compromise how large or how long we can run.
Clear. Yeah, thank you. Very nice, very interesting. Okay, I don't see any questions from any of the attendees. I think it's a very, very clear, systematic presentation. Thank you very much. So I think if we don't have any more questions, then I think it remains just for me to thank you again for a very nice presentation. Yeah, and thank you, and thanks for everyone attending as well.
Thank you very much. Yeah, it's been great.
Okay.
Okay.
All right. Good afternoon, everybody. Great innovations.